So as we mentioned earlier with the main control unit, that we have control signals which has been derived from the instruction. The instruction types that we had, as you already knew, are type, load or store, and then branch, and also like jump and stuff like that. But as you can see that we have an R type and both of these are I type. However, we are dealing with them a little bit differently in the sense that with a load word and a store word, we are using these values to know from where I should bring my stuff and to where I should also write my stuff. But in the branch, from these two places, exact places in the instruction, I'm doing something else. I'm doing a little bit of kind of a comparison. For instance, if I'm saying branch equal, so this means that I'm taking that RS and RT and see if they are equal or not. If I'm saying branch not equal, so this means that the comparison that this or this is not equal or not. Less than, if it is less than or not, less than or greater or whatever, the comparison that I have to do is a little bit different than whatever I'm doing with the load word and store word. The other thing that the branch when I write an address here, as we have already explained, that this is basically the relative address, meaning whatever the value that is written here, in order to know where I should branch, I need to do program counter +4 plus 4 multiplied with whatever the address is here. Why we do multiplication by 4? Because we already explained and showed you that the word is 32 bits, which is 4 bytes. According to the default situation, it can change, of course, but for now, the word is 32 bytes by default, and accordingly, it is basically 4 bytes. And in order to do an implementation of multiplication by 4, this is basically shift left by 2. So if I would like to implement that, it's just shift left by 2 multiplied by that particular address, add that to the program counter +4. So now I know where I should go. However, the address here that is in the load word or store word, I'm just taking that address to know what is my shift is to add that value to the source register in order to know where is exactly the address. For instance, if it is load word S1, 8, S2, so this 8, which is basically here, I have to add it to that particular value that is inside that S2 in order like to know where is the location, and then I have to take that particular location and copy it to S1. Also, at the very beginning here from 26 to 31, all of these is just my opcode. Here, the first 6 bits, if it is an R type, it is a function, then the shift amount, and then the destination register is from 11 bits, 11 to 15, RT 16 to 20, RS 20 to 25. As you can see from here, that always RT is from 16 to 20, and always RS is from 21 to 25. So as soon as I have an instruction, I can say that from bits 16 to the 20th, this can be in RT. From bits 21 to 25, this can be allocated into the RS, for instance. Also from 0 to 15 can be located as an address, but here from 11 to 15, this is the RD. And accordingly, we have shown earlier our data path with control and how actually we can have an implementation that holds all of these blocks in order to implement a certain particular instruction. For instance, as you can see from here, here is just the program counter. This guy is the instruction register, which has all the instruction, that program counter will always point out to the next instruction to be executed. So at the very beginning, it's just like program counter, and then we'll go to program counter +4, meaning I'm going to the next instruction, program counter +4 going to the next instruction, and so on and so forth. As soon as I have my instruction, as soon as I fetch my instruction, so now I have 32 bits. I have now in my hands 32 bits. How I can read these 32 bits? I have to design my implementation accordingly. As we have shown in the previous slides, that each part of these bits means something. How we can implement that? As we have highlighted in the previous slides, that from 21 to 25, we'll refer to that as RS, which, as an example, I can say that this is read register 1. That guy here is an address that point out to where exactly my RS is. RS is in slot 1, slot 2, slot 3, slot 4, and so on and so forth. Slot 0, whatever any of these slots in the 32 available slots, for instance. As we have also shown in the previous slide, that from 16 to 20, I can refer to that as the RT. And again, this is the address of that particular one. And I can say like, okay, this is also register 2. Again, in that particular case, assuming now that I have an R type, I will assign this particular value to the RT. If I don't have an R type, I will take the instruction from the 11 to the if still I have an R type, I will take 11 to 15, and this is my RD, and my RD will appear here, which meaning the destination register, or where I should write my data. It's a destination register, so where I should write. Again, it is an address. If it is an I type, from my instruction, I will take the first 16 bits here, and then I will do sign extension in order to allocate them in a 32 bits. Why I have to do a sign extension? Because at the very end, it will go to the ALU, and the ALU is doing an operation between inputs that they are, in this case, 32 bits. So I can't add the 32 bits to a 16 bits. How about the other 16? The ALU will not guess what is the other 16. I have to do something. I have to force what are the values in the next 16 bits. And that's why I'm doing a sign extension. Sign extension means that I am writing the same exact number in a 32 bits instead of 16 bits. That's meant by sign extension. If this was an R type, so this means that I don't need the whole 16 bits, I just need the very 6 bits from there, which is referring to the function. And this guy will go to the ALU control, which will control what is the arithmetic operation needed from the ALU. So I'm looking at the very first 6 bits, and then I will go to the table and see like, if this is X number, what is the corresponding operation, and so on and so forth. Assuming still now that I have an R type, so as soon as I have the address of the RS, that particular location will just appear at the output. Meaning, let's say that I'm pointing out to slot number 4. As soon as I'm telling you that this slot number 4, please, from the output, take all of the data that is in that slot to the output. Fill out or fall all the balls to the output from that particular place. It's just like here, that is the slot number 5. Please open the door, then all the 32 bits will come outside. And that's why, in this case, of course, this is 32 bits. The same exactly apply with the second source. As soon as I know what is the second source, it will appear here to the output, which it appear to the ALU here according to my control signal from here. This control unit has the input of instruction from 26 to 31, which is basically the opcode. As soon as I know the opcode, then I will choose like which value in that multiplexer, but assume that I will choose that particular path, which will appear here. Now the ALU will do a certain operation, either addition, subtraction, multiplication, whatever, according to the data coming from the ALU control. Then I have the output. So I have added them, subtracted them, multiplied them, whatever the action that I have done. Then I have the output, where I should allocate the output. If you recall from the R type, we also include a destination register address. So this means that I'm telling you do an addition, for instance. Let's take that example, S1, comma S2, comma S3, meaning that take this as an RS, take this as an RT, and take this as an RD. So you will do addition and put the results here. How I will know that I need to put the results here? It is basically from that destination register address that is here. So I'm telling you, please write that in that particular slot. Which one of the slots here? How I will write that? I will write that through that particular connection, which is here. And then write data. So this write data, of course, I'm writing the whole 32 bits. Where I should write? In this S1. How I would know? From that particular address location. So when you write, I have to tell you like where you should write. I'm telling you here from that destination, please write that in slot number 7, for instance. Then I have to have a connection that will carry all of the balls to that particular place. And that's why I have this particular connection, which is 32 bits, which is writing all of the data to that particular 7th slots, for instance. So this is the path as an example if I have an R type. As you can see from here, although I had all of the components, I'm not using all of them. As an example, in an R type, I'm not using the memory at all because I'm not passing the memory. No matter what is the R type is, I'm not passing through the memory at all. There is no interaction with the memory. Also, I'm not doing any sign extension because I'm not dealing with the first 16 bits address at all with an R type. So I don't need that particular component, although I have already included in my design. But as soon as I see an instruction of R type, I'm just neglecting this component. I'm not using it. And of course, my code has to reflect these kind of things. Also, I always have my program counter +4. So whatever I have here is always updates of my next instruction as program counter by 4. So this will be my next instruction, and I no longer need all of these things, which will be introduced very short. So now with an R type, I know the RS, I know the RT, I know the RD, I know what is the results, I know where I should write, and that's all. And according to this, my control unit, it will control some of the components according to my particular instruction. If I have a load instructions, for instance, load word as an example. If I have a load word, then I will have again the RS, I will have the RT. There is no need for RD, but there is a need for the first 16 bits, and then I will do the sign extension. And then after that, I have actually to add that or subtract that to whatever I have as an RS. Because if you recall this 8 in the previous example, this 8, it has to be added to the S, correct? Whatever like that S register in order to know where is exactly the address inside the memory. So now I know the address, I have done the sign extension, and then I have actually to add both of these to the ALU, and then I have now the output. So this output is pointing out to the correct location inside the memory, which I need to grab my data from to copy to the register. So now I knew exactly where I'm going. I'm going to that particular address inside the memory. As soon as I am pointing to that particular address, that particular location has to come out from the memory. And that's why I have to read these data from the output. And then what I need to do is write this data to the register. Where I have to write this data into register? Through the RT. So I know exactly where I should write that from this particular location or from this particular information. So with this, I'm dealing with all of this stuff, and also program counter is program counter plus 4, and always I'm updating that, and I no longer need these components. However, if I have a branch instruction, for instance, a branch, as we have already highlighted, that I have an RS and RT, and I'm doing a certain particular comparison. So I have an RS and RT. As soon as I have the correct address, it will appear here. As soon as I have the correct address, it will appear here. This ALU will do a comparison. Let's say that is saying like if they are equal or not. If they are equal or not means I need to do a subtraction. If the subtraction is 0, I have to say yes, they are equal. So I will have a flag of 1, for instance. And that's why I refer to this as 0, but this will have a flag of 1, meaning that if they are equal, so this means that subtraction is 0, I have a flag of 1. Yes, they are. So the statement is true, then I will have a 1. As soon as I have a 1 here, so this means I know, of course, that this is a branch from my opcode and the function, and then I will have here a 1. So this means that I'm not choosing this path, I am choosing this path to update my program counter. As we have highlighted earlier, and we have shown you in the previous couple of slides, that actually this need to be updated as follows: program counter plus 4 multiplied by the address. Here is exactly what I am doing. This is program counter plus 4. This guy is shift left by 2, which is multiplication by 4. To what? To the address. The address is coming from here, which was already signed extended by 32 from my 16 bits. So I took the 16 bits, sign extended to 32. So now I have it in 32 bits. I have to multiply it by 4. That's why I have already multiplied by 4 here with shift left by 2. Then please add this to the program counter plus 4, add this to the program counter plus 4. I have the output, and then I'm updating the program counter accordingly. So I am going inside my instruction memory or instruction register to the correct location, to the correct instruction, because this is what I'm saying, that if they are equal, please branch to that particular location. And this is the implementation. And also, if I have a branch, I'm not dealing with the memory at all. That's why this is just dimmed. So as you can see, I still have all the components, but I'm not using all of the components in all of the instructions. Let's see an example of how we can write something like that with the Verilog. So assume that you will call your module a register file and write all of this information. You need to define first the input. So the input, read 1, read 2. This read 1, read 2. Of course, this is 6 bits, 5 bits and 5 bits. And this is what you have defined here. It is just 5 bits. And also, you are defining these, since this is R-type, write register also as a 5 bits. So write register also as a 5 bits. However, the write data is 32 bits, and that's why you are defining another input as 32 bits, which is this particular input, for instance. Also, I have a register write. This data is just like 1 bit, and that's why input register write. I have also the input clock. You can write clock, I mean, here it doesn't matter. However, in the output, I have 2 output. I have this output and I have this output, which each of these are 30. Each of these is 32 bits. So output, data 1, data 2, 32 bits. I also need to define my register. This is my register. This register is what? 32 by 32. I will define it as a register 32 by 32, and I will call this as register file, for instance. Also, I'm using here an assign statement that assign the data 1 to the register file at this particular address and data 2 to the register file at this particular address. Why? Because this data 1 and data 2, it's basically, it appears here whatever that address is referring to, and it appears here whatever that address is referring to. So as soon as I'm telling you here as an example, take slot 5, this slot 5 will appear at the outside. I'm telling here slot 4, this slot 4 will appear at the outside, and that's why I'm assigning this accordingly. And I may say, okay, now I will begin my always block. As soon as I have a positive edge clock, please begin. As an example, if I have register write, please write inside my RF register at that particular address, whatever I have in the write data. And then end the module. It's just like showing you an example of how to define something like that. You can also do that by this behavioral implementation with multi-cycle MIPS design. For instance, I can define a load word with these bits. How I would know these bits? Go to the tables, what that number refers to. You'll find that this is equal, store word with this, branch equal this, jump this, and so on and so forth. Input clock. I will define also my program counter as 32 bits. My RF or the register here now, again, as 32 by 32. My memory is like as big as that. And then I will define also some other inputs. I can define also if I would like work with a state machine that I have like a state, and this is, for instance, from 0 to 2, meaning that my states here can hold up to 3 bits. And if it can hold up to 3 bits, so this means that I can hold states from 0, 0, 0 all the way till 1, 1, 1, meaning that I can have up to 8 states. So I can build actually my design as a state machine. And in this case, if I'm saying from 0 to 2, that means that I have 8 states. I can define also a wire that is called opcode, which is 6 bits. I can define another wire that is 32 bits as the sign extension or the program counter offset, for instance. I can use also the word assign here to assign things that does not basically relate to my always block, meaning that is always there. It's not like sequential. It's always there. As soon as I have my instruction, these bits from 26 to 31, for instance, has to be in my opcode. In order to do a sign extension, what I'm doing with a sign extension, I have from 0 all the way to 15, as an example, my bits. I have to write that into 32 bits instead of 16 bits. How I should do that? As we have learned earlier, that I'm taking that value and I'm just repeating it 16 times. So if these ones, I'm repeating the ones here 16 times. If this is zeros, I'm repeating the zeros here 16 times. So meaning that I'm writing the same exact number that was written in 16 bits in 32 bits. That's all by sign extension. How I can write that in Verilog? Here is the example. Please take from 0 to 15, and then take the 16th one, which is number 15, and repeat it 16 times and concatenate that with the first 16 bits. This is how it will be written in Verilog. Also, the program counter offset, in this case, according to this definition, is just sign extension multiplied by 4, which, as we have seen here, that I'm taking the sign extension from here, the output, and then I have to multiply it by 4. I call this program counter offset, whatever I have here as an input, for instance. So sign extension, and then shift left by 2, meaning I'm multiplied by 4, and we have explained why we need to do that. Then, just at the beginning, program counter is equal to 0. I am at the very first state, always block at positive edge clock. Please we would like to begin and assure that the 0 location inside my register file is equal to 0. Why? Because if you recall, we have agreed that inside my 32 slots, the very first slot is equal to 0. It has to equal to 0. It has the 0 register. So I have to assure that this very first slot is equal to 0. And that's why I have this particular step. Then I will define like a state and then case state. If it is 1, please begin allocating I in my instruction register, whatever like I have in my instruction memory at that particular location. And please, I would like you to think why we wrote it that way. And then please update it, the program counter +4, and then go to the next state. As soon as I am in the next state, for instance, please, A and B is allocated as follows. By the way, this will be the RS and this will be the RT. The RS is just like whatever I have from the instruction at that particular location. In the RT, whatever I have in that particular location, and then go to the next state. And please, the ALU output will be updated accordingly, assuming that I have that particular value with the branch, or whatever like the value that I have in case that this is actually is off and it is equal to 0, depending on the instruction. And then I will go to the next state. This is 4. Now I need to do the load and store execution. I need to write a little bit more information. For instance, if my opcode is equal to load word, or my opcode is equal to store word, please, my ALU output is equal to my A plus the sign extension. Why? Because you recall from here in my load instruction, this is, if this is RS, so this is A. So this means that whatever is pointing to A, so whatever that is will appear here, and I am adding that to the sign extension. So I'm adding these both together, and then the ALU output results will be equal to that. And that's why I'm having here the ALU output as A plus the sign extension. But if my opcode is all zeros, I will know that this is R type. If you go to the table, you will know that as soon as my opcode is equal to 0, this means that I have an R type. But how I would know exactly what is the function of that particular R type, I have to go and check the very first 6 bits. Because the very first 6 bits, it will let you know if you have to do an addition or subtraction or multiplication, and so on, according to that particular number. So for instance, if that very first 6 bits has the value of 32, please go at the table and you will find that actually it is doing that the inputs of A plus B, for instance, in this particular case. You may also define a certain default that ALU output is equal to A and so on and so forth. In the case, I just would like to highlight that this is just one of the cases, but you may check your table or whatever like the implementation that's required from you, and you may add more. This is just if 32. However, whatever if it is like another number, what I should do, and so on and so forth, is just you need to add that in your code. If your opcode is branch equal, I just would like to remind you that this load word, store word, branch equal has been already defined at the very beginning of your code here. So if it is branch equal, then you will begin and check if A is equal to B or not. If A is equal to B, please update your program counter according to the idea that we mentioned, which is program counter +4 plus the program counter offset, and the program counter offset is not but the sign extension multiplied by 4. So you need to apply that here. However, if the opcode is equal to J, which meaning that I have a J type, I'm just implementing whatever we have mentioned earlier with a J type, that the first 2 bits is 0, 0. Then I'm taking all of the address, which is 26 bits, and then I am concatenating the value of the program counter from 28 to 31, as mentioned earlier. Then I will go to the right of the ALU. Again, if my opcode here is R-type, please, whatever I have in the ALU output, write it to my register. But where I should write that? How I would know? I need to go and check what is the destination register. Yes, so this means that basically here I need to choose the bits that correspond to the destination register, and then I will write that bits there. If you recall, the destination register is here. So this means it's from 11 to 15. So that's why what you need to do is basically right here from 11 to 15 in these particular locations. If the opcode is load word, please write whatever you have in the memory at that particular location to some intermediate like registers we'll call like this MDR. If it is a store word, please store whatever you have at that particular location in the memory, whatever you have in that register to that particular location in the memory. Then the fifth step, if you have a load word, please take or write whatever you had from the memory earlier from the previous slide to that particular location, which is showing you where exactly you have to write. This is, if you remember, refer to the RT. And then end the case, end the module, and stuff like that. Another way that you can write this also, that you can have the always block, and inside the sensitivity list here, you have a certain instruction. So whenever there is a change on the instruction, then you will basically instantiate like all of the stuff inside this always block, and then begin. If my opcode is equal to that, this means that this is R type. Please go to the function. If the function do this, then do the addition, and so on and so forth. If it is if it is equal to another thing, it is subtraction. Another thing is multiplication, and so on and so forth. And then you will define another case, opcode. If this inside the opcode, please do the load word, and so on and so forth. You can design also your code according to this implementation as well. You may also choose to do that totally differently. You may need to define like each blocks alone, and then begin to connect all of these blocks. So there are like many different ways to do the implementation of your design. As an example, I showed you here like these two examples. So then we need to think about, okay, more about the implementation and how we can choose our clock period, or what is the clock frequency in this case. First of all, in order to know that, I have to calculate the critical path, which is the longest delay in my design. This will control my clock period, because it's not feasible to vary the clock frequency with different instructions, meaning I will not take that instruction with this frequency and then that instruction with another frequency, and so on and so forth. Usually I just have like just one clock, and I'm dealing with this particular clock. As we will explain later on, that we can actually enhance the performance by using something called pipelining, and we will introduce what does that exactly means. But first, try to think about the critical path and how we would basically calculate the critical path. And accordingly, we will calculate the clock. The critical path, again, what is the longest delay? And according to that longest delay, I will define my clock period, which is basically the frequency. So in order to do that, let's follow these steps. First, assume that all of these stuff are negligible. Delays for multiplexers, control unit, sign extension, program counter access, shift left 2, wires, setup, hold times, and so on and so forth. But any instruction and data memory, it will take 200 picoseconds. Anything in the ALU and the others, it will take 200 picoseconds. Anything in the register file access, it will take 100 picoseconds, either if it is read or write. And according to this information, we need to see if I have an R type, how much will be the total time here consumed. If it is a load, if it is a store, if it is a branch equal, if it is a jump, and according to these values, I will know what is the longest, and accordingly, I will know what is the critical path, and then I will define or choose my clock period in this case. If I have an R type, I know that I have to access the instruction memory. In this case, I have to access the register. I have to access my ALU. I don't have to access the memory, but I have to access the register write, because I will take two. I will go to the instruction register and then take the RS and the RT, and then we'll do the ALU, the addition or subtraction or whatever the operation, and then I will write that output to the register, but I don't pass the memory at all. And accordingly, I will have these values. So this is 200, because here I have 200. This is 100 because I have this value 100. This is ALU 200 because I have the value 200, and so on and so forth. If you add all of these, you'll find that this is 600. With the load word means what? I will read whatever like the address from the register, and then we'll go to the memory to grab that particular location and copy that to the register. So this means that I will access the instruction memory, I will access my register, I will do an ALU operation, because in order to calculate the offset, I have to add or subtract. I will access the memory, and I have to write to the register or copy to the register whatever I had already brought from the memory. So this means that I'm using all of the steps, and accordingly, if I do the addition, I will find that this is 800. Similarly, with the store, I will go through all of the steps except the very last one to write to register. I will not take that into consideration, because store word means I will take value from the register and write it to the memory. So I don't have to write it again to the register. So the very last step will be the memory, and that's why I don't have this. If you do the addition, you will find that this is 700. With the branch equal, you are accessing the memory, register, ALU, and that's all. You are not accessing the memory, and you are not accessing also the register write. In the jump, you are just accessing the memory, and none of these you are basically dealing with. You have to take into consideration that in this case, we are neglecting all of these kind of operations. Again, this will be 200. If you look at all of these numbers, you will find that the maximum is 800. 800, in this case, picoseconds. Accordingly, I should decide that my clock period will be equal to 800. Okay, that's fine, but what will be the drawbacks in this case? Let's see how we should think about it. Assuming that this is now the 800 picoseconds, same 800 picoseconds, because we will stick with just one clock value. So the load word will take all of these 800. But for instance, the store word, as you can see from the previous slide, that this is only 700. I have waste of 100. If I have a jump, the jump will be here for 200. And then all of these will be waste. If I have a read will be approximately 600. And then all of these will be waste. So unfortunately, although I can satisfy the critical path, but I am wasting time in all of the other instructions that is taking less time than that particular critical path. So just like think about like a program that has 2 load word instruction, and all of the other instructions are either R type or jump. However, because of these only 2 instructions, you are forced to go with the critical path, which is 800 picoseconds. You can imagine how much waste do you have in this case. So we need to think with a solution to solve this kind of problem, how we can satisfy the instructions with the critical path of the longest delay, and at the same time, not wasting a lot of time. Or at the same instance, not losing a lot of time. So we need to think properly how to do that. So this basically called for the pipeline implementation. With this pipelining implementation, we can handle this kind of problem in a very nice and neat way. So with this explanation here, with the kind of pipelining implementation, we would see first how we can implement pipelines in a laundry, and then we'll see how we can apply this to our condition. So assume right now that you went to a laundry, and then first you put your stuff in the washing machine, and then after it finishes, you just use the dryer, and then you begin to fold your stuff, and then put that in a nice place. Then the next one will use the exact same resources, begin with the washing machine, dryer, folding, and then dressing and stuff like that. Then the next person do all of these things again, and then the fourth do all of that again and again. So if we were to think about beginning at 6 p.m., 4 persons will finish at 2 a.m. However, there is an intelligent and smart guy among these 4. He had said, okay, why we are following these steps that way? How about think a little bit smartly, and as soon as the first guy will finish the washing machine and go to the dryer, let's jump into the washing machine since it is already empty. Then I can use it. And we'll follow that particular smart idea with all of the others, meaning that as soon as the first will leave the dryer and go to the folding, then the next guy can go to the dryer, and then the third guy can jump into the washing machine, and so on and so forth. So if we were to begin at 6 p.m., interestingly, we can finish at 9:30. So we can take just 3 hours and a half. And if we would like to calculate the speed up between this and this, we will see that this is 8 divided by 3.5, so it is equal to 2.3. So this guy is 2.3 times faster than this guy. But this is just a small idea. And this is the pipeline. We need to think by analogy. So first, we have also to have or to implement stages in our design. As analogy to the dryer, to the washing machine, dryer, folding, and so on and so forth, we need also to have a couple of these stages here. So we will have the first stage at instruction fetch, and then I have to decode, and then execute, and then memory access, and then write back. So this is, for instance, like the washing, dryer, and so on and so forth. This is the next one, and each of one of these is holding a certain clock cycle. According to that, and according to these things, so this is clock cycle, clock cycle, clock cycle, clock cycle, clock cycle, and so on and so forth. If you were to choose what is the period of the clock cycle, you will see that if you were to choose this as a 200, then you will satisfy all of them, because here all of them are 200. Here all of them are 100, which is less than the 200. So you can still satisfy them with the 200. And they are not losing a lot of wasting time in this particular case, because the maximum waste will be just 100 picosecond. With this guy, still 200, all of them 200, 200. With this guy, 100. So if I have all of these 200, it should be okay. So accordingly, I will choose that clock period that way. So by analogy, if I were to go without a pipelining, so this means that I will take that first instruction, I will do the fetch, and then then access the register, and then the execution, and then the memory, and then the very last register. All of these has to take 800 picoseconds, and then I will go to the next instruction, then I will go to the next instruction, and so on and so forth. But with the pipelining idea, as soon as I finish fetching the first instruction, I will go to fetch the second instruction while I am dealing with the register of the first instruction. Then the next step, as soon as I fetch the second instruction, I will go to fetch the third instruction while I'm dealing with the register in the second instruction, and I am with the ALU in the first instruction. So for instance, I am using here the folding, I am using here the dryer, I am using here the washing machine. All of these at the exact same time. With this idea, if I begin here, I will finish here. As you can see, finish here, comparable to this particular implementation, I still didn't even finish the second instruction. One more thing I would like to highlight, as you can see from here, the register is taking half of the time, because as you see in the previous slide, that this will take 100 picoseconds, while this actually is 200 picosecond in this particular case. So in order to get a sense of the pipeline speed up, you can follow this formula. The time between instruction in the pipeline case equal the time between instruction in the non-pipeline divided by the number of stages. Meaning that under ideal conditions, and you have a large number of instructions, the speed up from pipelining is approximately equal to the number of pipe stages, meaning that this guy is equal to this multiplied by that. So if you were to have a 5 stages pipeline, this means that it is approximately 5 times faster if I have a huge amount of instructions. Roughly, of course, roughly. If I have a 5 stages, so this means that I am implementing that particular code 5 times faster than the normal implementation. So now going back to the same implementation that we have highlighted earlier, but with another sense. As this first step, I will call this as fetch. I will call whatever is happening here, register and sign extension, all of these as just the code. Whatever is happening here is just execution. So here I can do addition, here is an ALU. All whatever is happening in this particular case is an execution. Whatever is happening here, I'm dealing with the memory. Whatever is happening here, I'm writing back to the register. So now I have divided these into partitions or stages. But the problem that I may face here in my implementation, that while I'm going from a stage to stage, I may lose some of the information, meaning I have to have actually a register in between these stages to carry the information to the next stage. While I'm finishing this, just carry it to the next stage. And accordingly, I am adding these registers in between these stages. As you can see from these registers, it has an input here as 32. It has another input here as 32. So this means that this is 64 bits. This guy has an input here of 32, another input here of 32, 32, 32. So this means that this is 4 multiplied by 32. It has to carry all of this information. The next one, this guy is 32. this guy is 32, this guy is 32, but this guy which has a 0 is just, as I mentioned, a flag, either yes or no. So meaning that it will be either 0 or 1. So this is basically just 1 bit. So the size of these will be 3 multiplied by 32 plus 1. In the next one, I have here this as 32, these as 32, 2 multiplied by 32, in this case, will be the size of that particular register. It may differ, of course, in other cases, but for that case, it is as I have already shown you here. So with this pipeline operation, I can look at the diagram as a single clock cycle pipeline diagram, or I can look at that as a multi-clock cycle diagram. Let's begin with looking at that as the single clock cycle. So if I have this, it is a single clock cycle. At that particular clock cycle, I am fetching. The next clock cycle now, I am decoding. The next clock cycle, I am execution. So I took one instruction, and I'm just showing you how that instruction will pass through the different stages in my data path. It is the same instruction, the load word, as I showed you here. If you recall, this is load word. It's still the same load word, same load word, same load word, and then this load word at the right back. But with this implementation with the right back, unfortunately, there is a problem. There is a problem if I would like to write back whatever I have here from my memory to the register. So what is that exact problem is? The problem that when I went through all of these steps, and when my load word actually is here, the data that is inside this stage, or the instruction that is inside this stage, is already something else. This is not the load word. If you recall from the very beginning, I have here the load word. As soon as I go here, there is another instruction actually that fetched in, and then as soon as I go here, there is that instruction that were already fetched in is now in the decoding stage, and there is a new guy went to the instruction fetch. When I go there, again, new one, here I had the very first one, and then the next one, and so on and so forth. When I am here, as you can see from all of these things, that I had, at this particular case, when I am decoding, another instruction. So the problem that as soon as I will look at these values, especially where I should write, at this time, if I were to write with this particular register value, I am writing to the wrong location. Why? Because this particular write register, it is just like decoding that instruction. And accordingly, there is a high possibility that that value is not similar to the value that I had already from the load word. And accordingly, I'm writing to a wrong location. So how I can solve this problem? So then actually I have to carry out with me, while I'm going with this pipeline implementation, that particular address location, or with another sense, where I should write. Because now, if you were to be at this particular stage, it is a wrong register number. But if you were to carry this information with you, what exactly or where I should write, then to the next step, to the next pipeline register. So when you are writing here, you know exactly where to write according to the value that you have here, and then there should be no problem with where exactly you need to write. So this kind of things with the pipeline, as you can see, yes, we are getting a higher throughput, meaning that we can actually implement larger number of instructions in a shorter time, but we began to see like some drawbacks. There are also other drawbacks that we will go through and we will cover, but these just like one of them, and we have introduced like how we can solve that issue in this particular case.